RSC Advances is the RSC's largest journal. It's also the largest open access chemistry journal in the world at the moment. In 2018, we had submissions from over 80 countries and we published articles from over 60. We've got about 100 associate editors from over 30 countries across the world, so we're really a global community publishing in all areas of the chemical sciences.
The main advantage of RSC Advances is the fact it's open access. Once you publish that paper, anyone around the world can access that paper and read it.
We really make sure that our authors get high quality reviews, and we try to get our papers to publication as quickly as possible. So we think we offer a very good service.
We have an exceptional team of associate editors who work closely with the research community, who solicit reviews from trusted reviewers to help evaluate work.
The first important thing about submitting a paper is ensuring that you have a really good cover letter that clearly explains, the novelty of your approach and the advancement of the science, because that is the first thing the editor is going to read.
For authors who want to submit to the RSC, my major advice would be the same advice I give my PhD students. Keep it simple, keep it focused, and really make sure that you're providing the evidence, the scientific evidence to support your hypothesis.
I think one of the things that sets the RSC apart from other publishers is that it's really more of a family type community. The RSC is not this behemoth publishing entity. I think one of the things that I have found refreshing is how they really try to engage the younger scientific community as well in all aspects, not just in publishing, but in terms of board membership, in terms of the types of symposia that they support, and the ways in which they try to support diversity and inclusion.
The RSC is a society publisher, and that means that it has its members at its heart, it has its authors at its heart, and it puts back into the community. So I would recommend RSC Advances because of our open access model. I think open access is very important for disseminating research, for reaching your colleagues and your collaborators, and RSC Advances has really pioneered the use of open access.
I think we'd really like to engage as many people working in chemistry as we can, really get people excited about open access publishing, making sure that people have access to as much of the chemical sciences research as they can.
Okay, welcome everyone, and where's my Zoom?
Hello, I'm Jill Reid. I'm Professor of Inorganic Chemistry at the University of Southampton.
Okay. Where's my Zoom? Okay. Hello everyone, and welcome to the first seminar of WeSST. Thank you for joining us. Today we will hear from Professor Rob Carpick and Dr. Stefan Eder. And we wouldn't be here if it wasn't for our sponsors, so we would like to first thank the Royal Society of Chemistry, the Institute of Physics, the Institution of Mechanical Engineer, and Swiss Tribology, which made this possible. So this will be a series of 6 seminars. The first one being today, and then ending at the end of June. And there will be a Twitter poster conference on the 11th of June, which I really encourage you to take part in, because it's a great way to really show your research. So today, obviously, you can't just raise your hands to ask questions. But there's 3 ways that you can interact. The first one is what I already see some people are using, which is the YouTube chat. And then if you're not logged in YouTube, then you can just send us an email at contact@westtribal.com, or you can tweet us using the West 2020 hashtag. So that's all the housekeeping. So now we can start. So I would like to introduce our first speaker, Professor Rob Carpick from UPenn, and he will tell us about his work on surface science of tribochemical interactions. Over to you, Rob. You should unmute yourself.
There we go. Can you hear me now?
Yes. Yes.
Good. Thank you very much. All right. Well, thank you, James and Chiara, for organizing this. This is a timely event. I think the community is hungry for discussing research, and it's nice to be connected around the globe, I think, by people joining. So thank you for your efforts. And hello to everybody who's listening in. Thank you for joining. I'm going to tell you about some work we've done studying tribochemical interactions using in situ methods, namely in situ atomic force microscopy. And key motivation to this within tribology is in trying to develop better lubricants so that we can address the massive challenge of energy consumption in automotives, as well as in machinery, in manufacturing, in any system where you have moving mechanical parts. We all know as tribologists that there's a lot of dissipation of energy due to friction, as well as damage due to wear, which causes problems with reliability, with safety, and we want to see what we can do to improve this. And one of the major thrusts in industry for some time now has been to try to enable the use of lower viscosity lubricants, because of course you'll reduce the viscous drag as the lubricant moves through the system, the churning losses that exist in the mechanism, including in car engines and in gearboxes. But of course the risk is this: as you move along the Streibeck curve here, if you lower the viscosity, of course you lower the friction, but you start getting boundary contact at points of contacting moving interfaces. And
sorry, Rob, can I interrupt you? We're seeing your presenter's view. Maybe
okay.
If you could switch to the bigger full screen view.
Okay. How about that?
It's still presenter's view.
Okay. Hold on. Let me try to share again to make sure I'm getting the right version. Okay. How about that?
Yeah, that's great. Thank you.
Okay, thank you. All right, so of course, to deal with these boundary contact issues, we have friction modifiers and anti-wear additives to reduce friction and wear accordingly, in addition to all the other additives that are in the lubricant. But if we're going to try to design better lubricants and better additives, it would be beneficial to study these at the nanoscale. And so the way we like to do that is using atomic force microscopy. So what I'm going to talk about today are a couple examples where we've studied the way additives behave when studied using the AFM. The advantage of the AFM is that you get a single asperity nanoscale contact. So you've got a controlled geometry, you know or can calculate the contact stresses, you can model and understand this clearly, and you can image with high resolution to see what you've done, to look for wear, to look for surface modification, to look for tribofilms. Of course, there's still a big step needed to go back up to the larger scale. You still have to think about the multi-asperity contact that happens in real contact. But our goal that I'll focus on today is at least determining some new science and new insights working at the nanoscale. So this work, the first part of the work I'll talk to you about concerns using ZDDP, work largely done by Nitya Goswami, Filippo Megalini, Jaron Ma. It was a collaboration with ExxonMobil, Dalia Yablon now at Surface Care, and Andy Konachek participated in this work, and these are some of the publications that have come out of it. So I'll talk about this older work from a few years ago as an introduction, and then tell you about some newer results. ZDDP is this famous additive that works very effectively as an anti-wear agent, also as an antioxidizer, and it helps prevent wear at points of severe contact in engines. It's used universally in engine oils, and the way it's known to work is through the breakdown and absorption of thermal decomposition products of ZDDP that absorb onto the steel and metal surfaces, and under the action of the contacting stresses, they react with other molecular fragments of ZDDP, and they start to build up a solid-like film that acts as a protective film on the surfaces wherever contact takes place. So this has been used for decades, and it's extremely effective, and it's also a cheap molecule to produce. However, it has some issues. It degrades the catalytic converter due to the phosphorus and sulfur content. It actually increases friction a little bit. It also doesn't work if the temperature is too low or if you have pure rolling. You need some shear. And if you have stresses that are too high, too extreme, the films don't stand up to that. And as well, they don't form as well on certain substrates as they do on steel, like aluminum, lightweight aluminum-based alloys. So that means that we would like to reduce or replace ZDDP by finding alternatives. And to do that, a good place to start is to understand better how ZDDP works. So we have been using, well, first let me quickly review what's known about the classic mechanism of ZDDP. And Hugh Spikes has a nice review article from 2004 covering this. We know that wherever you slide, you get these patchy films made from these reactions, products of these ZDDP molecular fragments that build up. And by having this protective film on the surface, just a few tenths of % of ZDDP in solution will greatly reduce wear of steel and many other materials. The growth rate increases with temperature, so there is definitely thermal activation of the chemical processes occurring, such that below about 50 C, you don't see much growth of useful films. You only see growth where there's sliding. You need shear, not just normal pressure, not just rolling contact. And the films form these patchy-like structures. They sort of form continuous pad-like structures separated by valleys, whose structure has a graded composition and graded properties. It's a glassy phosphate with sort of a thin outer layer of zinc polyphosphate, and it grades to shorter chain phosphates deeper in the bulk with some sulfur that's clearly helping attach it to the surface. It grows to anywhere between 50 to 150 nanometers thick, depending on conditions, but then levels off. And that's a great property because you don't want this film to grow forever to deplete the solution and to maybe jam up the small gaps in your components. It ends up limiting itself through ways that were not so clear until recently. And there's been a lot of excellent work. I'm pointing out a few studies of discussions of the role of the substrate, including debris particles from the substrate, potentially catalyzing growth of these films, and work largely led by Martin Muser and colleagues, where they showed using quantum chemical calculations how stress has a strong effect on catalyzing the interactions that occur. So to get at this more deeply, we decided to do some in situ tests using AFM in single asperity contacts. The advantages of this method in general are that you can use almost any substrate as well as a variety of tip materials. You can work under fluids, you can vary the temperature, you can have a range of stresses that can reach very high values to match experimental conditions, and you do have a range of speeds, although they tend to be quite a bit slower than the macroscopic applications. And you do this all in a nanoscale single asperity contact, a well-defined contact where you can measure topography and control the load, measure friction, measure wear if it is occurring. So this approach that we introduced a few years ago now involves essentially using a fluid cell, or you can also use a film or even a droplet. You have your base oil, you have your additives like ZDDP in it. We have a heater in our AFM, and we use, say, iron or steel substrates. And you can run the AFM under this immersed condition with the additives present. You can slide in a confined zone to try to create your tribofilm or surface modification, and then you can zoom out and image it separately later. So it's just a cartoon illustration. If you slide several times, these molecules are being trapped in the contact. They're experiencing these compression and shear forces. They're reacting with each other, and they build up these films. So tribological stresses are assisting the chemical reactions to drive the growth of these tribofilms. And here's just an example of playing around. Here at a load P1, you get some film building up. Here, a higher load, but same number of cycles, a thicker film, even thicker film at a higher load P3. So you can essentially dial in and draw these tribofilms where you want them. And you can track the growth by periodically measuring the height and width of these films. You can track the volume of the film as a function of the number of scans. So this is just one example of many. We do these experiments at different stresses, different temperatures, and we track this rate of growth. And from that, we can get a reaction rate. Okay? And if a reaction follows Arrhenius kinetics, then you expect that reaction rate to vary exponentially with the free energy of whatever the barrier is to this reaction. Now, Bell and Eyring showed how force or stress can affect the energy barrier to such reactions through this framework of mechanochemistry. They postulated that you have a linear effect, a linear change in the activation barrier with the applied stress. And if you plug that linear dependence in, you get a prediction that the reaction rate should vary exponentially with the applied stress. So on this energy diagram over here, what we're saying is the stress you apply multiplied by an activation volume, which represents the volume that's being affected by the stress that drive the reaction, reduces the activation barrier. So you get this exponential benefit from applying stress. Now, I'm going to talk about normal stress, but I want to point out, and I have a citation on another slide, that Hugh Spikes has done some nice work showing that shear stress is likely the driver in the case of ZDDP. Normal and shear are correlated in our sliding experiments, and so we think that what we're seeing here also are shear-related effects. So here is how that growth rate changes with the contact pressure. So these are a series of experiments. Each one, the load is kept constant, and this is the initial contact pressure we apply based on using contact mechanics to calculate it. And what we see is as we increase the pressure, there is indeed a rapid increase in the rate of growth up to a point where then it eventually sort of doesn't increase much anymore. And if you take a look at, if you plot on a log scale, indeed you see there's something consistent with a linear law using this, again, Arrhenius or Eyring-like model from which you can pull out an activation barrier of about 0.8 electron volts. That's reasonable for sort of covalent bond-like interactions. And you can get an activation volume of a few cubic angstroms, which is reasonable for a molecular scale process. And just to show you what this looks like, we're holding all of the conditions constant: temperature, the materials, the concentration, the numbers of cycles. We're just changing the load as we do multiple replicate experiments at different points on the substrate. And what you see is clearly stress leads to a thicker average film. There's also roughness here and topography. So we see a patchiness to the film, just like is known to exist at the macroscopic scale. If you grow the film at too high a stress, you do get a film, but you also see this competition between growth and removal. So here is this zone here where there was some film that then was removed, and you can see some pileup from moving that around. You can see no longer a clear exponential benefit to the stress because now this other process of wear, removal by the sliding is taking place. So that helps shed some light on what might be going on. So let's think about what this means for the growth of the film. If I calculate the stress I would get for a tip on steel at 100 nanonewtons load, I'd get about 2.6 gigapascals for my AFM tip. If I now let that 10 nanometer film, let the film grow to about 10 nanometers, using literature values for ZDDP tribofilms, there's a range, but say around 70 gigapascals is a reasonable value. After just 10 nanometers of growth, the mean Hertzian stress, according to continuum mechanics, has dropped to about 0.8 gigapascals, dropped by a factor of 3. Now remember, stress, the growth rate depends exponentially on the stress. So that translates to a 20 times lower growth rate of this film. We think that this stress-activated growth is the key explanation for why the growth drops off, why it attenuates with time, why it levels off at this 50 to 100 nanometers. As the film grows, it is cushioning the stress coming from the tip, the load coming from the tip. The stress reduces, the rate of growth reduces. So that strong dependence on contact stress leads to this leveling off of the growth. We think it also is behind the change in composition of the tribofilm as it grows. As you go through the thickness of the film, we know that its composition is changing. And we think that's related to the fact that the stress is different at different thicknesses, leading to different pathways or different degrees of completion of the chemical processes that occur during the sliding. There's been some nice modeling from Rob Bozeman's group showing that the results we get can be plugged into sort of a kinetic model. There's been some nice work out of Leeds University where they have also applied this AFM method for different forms of ZDDP, different additives, and they're also able to use this technique. So we think that this is a fairly versatile method, and we're interested in encouraging others to use it and apply it. I mentioned earlier which stress component matters, and I refer you to this nice recent work from Hugh Spike's group showing, in fact, shear stresses are clearly associated with the growth of ZDDP films. We wanted to, and that's something we're currently investigating further, but something else that we've looked at recently is addressing this question of whether tribofilms from ZDDP can grow on aluminum-based materials. As I mentioned earlier, this is difficult macroscopically, and it's a key limitation. You know, aluminum-based alloys are very promising lightweight materials, but if you can't grow these ZDDP films on them, then you've got a problem with your wear protection. So Martin Muser's work back in 2005 attributed this lack of growth on aluminum to a mechanochemical effect. Aluminum is a soft material. It will give way and deform before you may be able to reach the stresses that are needed to cause the tribochemical growth to occur. Again, exponential dependence on stress, that means an exponential dependence on the strength of the substrate and the stresses it can support. So that's one possibility. So to investigate this, we looked at both aluminum and aluminum oxide, in other words, sapphire surfaces. So this is the friction coefficient versus time. And here's the time and the number of scans. And these are the topographic images of the tribofilm as it's growing. And what we see initially is sort of a fluctuating tribofilm that eventually sort of stabilizes. And I hope you can see these bumps here. There's quite a bit of variation in friction that we're still working to fully understand. But clearly, you see these patches that are growing. These, we believe, are these ZDDP-based tribofilms that have finally grown on aluminum after struggling to do so at first. We see them on aluminum oxide as well. Again, we don't see much growth at first, but after some time, eventually we start seeing the nucleation of some pads, and then a stable tribofilm grows. And it only grows in the region where we've been sliding. These colored AFM images are from zoom outs from the sliding region. So we can grow ZDDP on aluminum and aluminum-based substrates, but then we're surprised, how was it that we got it on these materials? And in particular, we saw that there was a lot of damage to the aluminum substrate after the tribofilm had grown. You can sort of see some buildup here and sort of almost like a trench surrounding the tribofilm. In fact, what we observe is that the first part of the experiment didn't actually involve growth. It involved just deforming the aluminum substrate plastically. So while this does support that stress promotes tribofilm growth, the aluminum is soft. And when we look at it in the SEM, indeed we see that we have damaged the film. So this is damaged the substrate. So what you can see, this is where we were sliding with the AFM tip. And I should have mentioned, we used a large colloidal probe. So this is a much larger contact than a typical sharp AFM tip. So we used a microcolloid. We slid back and forth. You can see a lot of plastic damage on the substrate, sort of a dish-shaped indentation here, as well as a buildup of material, which is the tribofilm. And when we look at that in a cross-section in transmission electron microscopy, we see the aluminum, we see the tribofilm, and we see a lot of dislocations. So what that tells us is we first indented the aluminum. It then work hardened. Aluminum is a classic work hardening material. Its strength goes up as you move and compact and densify dislocations from deformation. So we think that what we were able to do was locally increase the hardness by the sliding action. And that's what led to the stiffening and strengthening of the substrate that then allowed the tribofilm to form. So there can be tribofilm growth on aluminum. You just have to get the stresses high enough, which means getting the aluminum hard enough. So we think stress is the key. Now there will be chemical effects. The bonding of this tribofilm to the aluminum may well be different. It may be probably weaker than on steel. Likewise, steel may also have catalytic effects. So the actual composition of this film may be rather different than what you get on a steel surface. But nonetheless, there is a film, and that's encouraging for understanding and perhaps adapting and working with ZDDP in these materials. But I mentioned at the very beginning that in the long term, we think ZDDP is limited, and we'd like to find ways to replace or at least reduce it. And so I'm going to tell you about some work looking at an alternative anti-wear additive as the last part of this talk. So this is work done largely by Harman Kare, who's now at Gonzaga University, Imen Luigi, now at École Mines Paris Tech, Nitya Goswami again, Zach Milne, current postdoc Megan Alinsky, and a current PhD student Parker Maskus, with Andy Jackson collaborating. And this is a collaboration with Pixelogen, a company based in Baltimore that makes nanoparticles. So they formulate these very monodispersed zirconia nanoparticles with an organic capping agent that allows them to be highly soluble in oils, including base oils or even fully formulated gear oils. They're very well dispersed. They're stable for months, actually years in solution. The solutions stay clear. And in these results from Argonne Labs from Nick Demas, if you slide or in a reciprocating rig or a micro pitting rig, you see tribofilms, and you see friction that's pretty comparable to the base oil. It's not much higher, it's not much lower. But they do see that you get films on the surface, and they have verified that these zirconia tribofilms will actually reduce scuffing and micropitting compared to a fully formulated gear oil. So just to show you what these look like, here's one of Argonne's tribofilms. Here's a cross-section using focused ion beam. Here's the steel, and sort of similar in character to the ZDDP, we see this solid, dense film built up on the surface. There's a nice sharp interface with the steel, and we see a very dense uniform solid. The zirconia has somehow compacted into a uniform film. It is not a porous, loose association of zirconia nanoparticles forming debris. This is actually a good solid film with very few observable pores. So what we think is happening is that nanoparticles are absorbing and being entrained into the contact. Through a process we're still working to understand, those capping agents are somehow removed, and the nanoparticles fuse together. It's almost like sintering of ceramic particles, assisted, we think, by the stresses that we're applying. So entrainment into the contact, shear-induced removal of the capping ligands, and then sintering of those bare nanoparticles to form films. And we even see in the TEM some coarsening or grain growth of the zirconia. There's a nice paper just this year from Steve Thrush and Alan Comfort at CCDC in the Army Research Lab, looking at this at the macro scale. we've done these nanoscale experiments, just like we did with the ZDDP. We're going to use colloid probes to have a larger scale contact. But again, we're going to generate the tribofilm and also measure its topography as we slide. And so here's a movie of the process. I hope this movie is working. Can you see that on the screen? Good. So it's repeating. You can see there's actually an induction period where nothing happens. Then eventually the nanoparticles start forming the film. They grow quite quickly, and then you see the growth levels off. You can see there's fluctuation. You can see this dancing of the topography. Both the average height of the film is fluctuating and the local height at different spots is fluctuating. So there is some exchange of nanoparticles, some attachment and removal at the top. But overall, that film remains. It is strongly bound to the surface. We are not able to scratch the whole film off of the surface. It's quite tenaciously bound at its base. So the film grows. We see sort of an induction period, then sort of rapid growth, and then saturation at a height. In this case, this is only 20 nanometers. It can grow thicker if we use different conditions. And this is a top view in scanning electron microscopy. Interestingly, not that different than ZVP, there is also a sort of pad-like structure, these bumpiness to the film. We can investigate the cross-sections of this film in the TEM, and again, we see dense polycrystalline nature, a well-fused film. We verify with energy dispersive spectroscopy that is largely composed of zirconium and oxygen. We see very little iron mixed in, and the carbon from the capping agent is removed. We see that the modulus and hardness of the film is close to that of bulk zirconia. So that demonstrates that the solidification of this film is quite effective. So that tells us, tribological stresses can be very effective at densifying and bonding materials together. Right? Interestingly, we do not see a thermally activated mechanism. When we vary the temperature, we see initially at low temperatures, we can actually grow these films at low temperatures, unlike ZVP. You can even grow them at minus 30 degrees. A rapid growth with temperature, but then just sort of fluctuations as we change. This is something we're still studying to work on. That's both the cycles to nucleation, and this is the growth rate that we measure. So we're still working to understand this, and it's work in progress. But we have a project continuing to work with Pixeligent, continuing to work with Argonne Labs to study more about the mechanisms and the interactions of these nanoparticles with other additives. As a final piece of information, we also see, like I said before, you can put the particles in the ZDDP tribofilms where you want them. So Harman Kari, former postdoc, made these patterns. He also made the pattern in my background, which is helping cover up my messy office. And so it's actually a nano patterning method as well. You can get lines down to 100 nanometers in width under controlled conditions. So to close, what we see is that, like ZDDP, we can get tribofilms with solid nanoparticles. They are dispersed with ligands into the oil, but the ligands are stripped off and can form surface-bound tribofilms driven by the tribological stresses. We see that the films have properties approaching that of bulk sintered zirconia. We see benefits in terms of scuffing and pitting, macro pitting, even in a fully formulated gear oil. And that gives us some excitement about using this in applications. At the nanoscale, we see that we can get films with concentrations as low as 0.01 weight % at low temperatures. And we even see growth of films in pure rolling contacts at the macro scale. So there are advantages compared to ZVP. I didn't mention this, but the growth is also enhanced by surface roughness, which gives us more motivation to keep studying the mechanisms by which these films grow. So this work is published in these two papers, and there is a paper under review on the work on gear oil, which I hope will be coming to you soon. So with that, I'll be happy to stop and take any questions. Thank you again for joining.
Thanks very much, Rob. Thanks for a really interesting talk. I've got a couple of, we probably have time for a couple of questions from the YouTube stream, and then the others will be answered at a later date. The video will stay up for a few weeks. So first of all, from Jack Walker, what type of FM tip was used to achieve the loads for the ZDP on iron oxide work?
Very good question. So initially we used silicon commercial tips that were coated with diamond-like carbon. Those make those tips more wear resistant than pure silicon. Pure silicon is not sufficiently wear resistant. We have since, in fact, been moving towards other tip materials. Even the diamond-like carbon can wear out after long numbers of cycles. So we actually recommend using hard coatings on your tips.
Thanks. And another quick one from Ramin Agabebe. Can we distinguish between the contributions of shear and normal stresses from a chemistry viewpoint inside the contact?
Well, from the experimental point of view, obviously we get the friction we get. But what I only touched on briefly was we measure the friction while we're doing the experiment. And what we haven't looked at closely yet, we're in the middle of looking at, is how does the friction vary throughout the experiment? I showed you a couple plots of that. How does that correlate with growth? So looking at different loads, and how the friction changes is one way to look at that. But I think we need help from theory. We need simulations that can help disentangle what components of the stress tensor end up affecting the chemistry. And that, I think, is an important challenge for people in the modeling community that we would love to see addressed.
Brilliant. And on that note, we have some such person from the simulation community. So I'll let Chiara introduce Stefan. Thanks again, Rob. Really appreciate it. Great talk. Thanks.
Thanks very much.
Thank you very much again. And so our next speaker is Stefan Eder. He works at ACTT and the University of Wien. And he is a simulation person of friction at the nanoscale, and today is going to talk us about exactly that. So use large scale atomistic simulation tools to explore sliding and grinding processes. So over to you, Stefan.
Thank you very much. Can you guys hear me? Okay, we're good. So good afternoon, good morning, good night, wherever you are. Thanks to Chiara and James for inviting me. What a great idea in these times. And this was actually the first science spam that I ever felt I wanted to respond to. It's also a great honor to be in the inaugural session of this series and right after Rob Carpick. Wow, hot dog. So now that we've heard something about tribochemistry and powerful in situ methods, let's look at another important aspect of tribology, and that's material science. So over the next 20-25 minutes or so, I'll be trying to convince you that in this decade that has just started, molecular dynamic simulations will probably come to the point where they can be of actual direct engineering use. I'm going to put my mouse pointer on visible. Yeah, I guess you can see that now. So for the probably about 2 people among you who may not have heard of molecular dynamic simulation before, this is a particle simulation methods that tracks the dynamics of a bunch of atoms or molecules. It's usually a rather small number, microscopically speaking, and usually it's only for a very short period of time. So it has nano written all over it. But this is where it's currently getting interesting because we're coming to the point where computers are getting so strong, so fast, that we have systems nowadays that are borderline microscale in their nature. And we can track them for periods that are definitely of interest to chemists and material scientists. So today I'll show you a couple of examples how MD can help the material scientific crew to use MD as a magnifying glass, to use it as a stop button, a slow motion mode, a rewind button, and sometimes as augmented reality goggles. So in the first part, I'm going to be talking about abrasion simulations or grinding simulations with MD. While these are 2 very different things for, let's say, process engineers and tribologists, actually for the MD guy, it's pretty much the same thing. I mean, they have very almost identical boundary conditions. It's just that abrasion is usually something that you don't want, and grinding is something where you want to take some of the material off. And then in the second part, I'm going to be focusing on microstructure evolution in sliding systems. So yeah, here I'm going to be focusing a little bit, I'm going to be dwelling a little bit on some very recent work that I've been doing together with some of my colleagues, some colleagues from the TU and Daniele Dini from Imperial College, where we made so many simulations on polycrystalline copper-nickel alloys that we managed to set up a deformation mechanism map depending on the composition and the contact pressure, but more on that later. So, but first a little bit of history. Very recent history, and also actually, to be honest, really quite only from my perspective. It's sort of like a timeline, if you will, of how the computational resources that I, let's say, a run-of-the-mill scientist have available, and how that has evolved, and what that meant to the types of problems that I could tackle with it. So here, this is Anno Domini 2014. This was the first system that I considered a large-scale atomic system. That's 400,000 atoms. It's a meter 28 by 28 by 10 nanometer system. It's monocrystalline. The asperities are weird and steep and bumpy. So I got a lot of laughs, but I also got a physical review letter out of it, so I'm not complaining. The typical job size was about 10,000 CPU hours. Back then, that sounded humongous to me. Then we move on 2 years, and we took the remarks of the reviewers quite seriously. So we said, okay, we have to work on the surface. We have to get the work pieces to be polycrystalline. We have to work on the geometry of the abrasives, and so on and so on. And we wound up with a system that was 60 by 60 by 30 nanometers and 6.2 million atoms strong. We had to cut back a little bit on the simulation time, but still the job size increased to about 10 times what we had before. So 10,000 CPU hours. And by the way, if you want to know what that is in dollars, it's usually divided by 100 and you're about what this is in dollars. Yeah, so one job is about a kilo dollar. Then 2 years on, this doesn't even look like such a big jump in size. It is in the number of atoms though. It's 25 million atoms nowadays. And we could increase the number of nanoseconds that we can simulate a little bit. And this has roughly doubled the job size. The reason we needed to do this was we needed to get our grain sizes bigger. This system here is pretty much nanocrystalline. It behaves very, very specially. If you're interested in sort of at least qualitatively macroscopic behavior, you want your grains to be more on the good side of the Hall pitch breakdown. So you want to be more closer to 40 nanometers grain diameter. And this is what we could achieve with this type of system. And this is what a lot of today's talk is going to be about that order of magnitude. And nowadays, see, the system size hasn't increased at all, but the job length has. So, well, the only reason I haven't made a larger system is because I haven't had the time yet, and because there was not the stringent necessity to. But I needed to do a job that slid a whole lot slower than 80 meters per second. Most tribologists shiver when they hear 80 meters per second. Grinding people don't, but tribologists do. So I said, okay, let's try one that's really slow, but you need a certain sliding path to see things. So I went to 8 meters per second, and that job cost $10,000. It's ridiculous. So I'm keeping that data double and triple. Another way to use all this computational power is to model steel. Steel is more complicated. The interaction potential that you need to be able to model it is more complicated. The Tersov potential has many body interactions, has angle dependence, and that costs you about a factor of 5 to 10 in time. So again, we do the same size, but now we're doing, let's say, cooler materials, or we can go slower. Now, sometimes I tell people I'm into computers. Sometimes I mean that quite literally. Sometimes I'm in a computer. This is actually my new toy. This is me in the WeSST4 supercomputer. It just went into full-scale operation on the 1st of May. I've been testing it for 6 months now. That was 20 million core hours. It's currently the number 93 in the top 500 list of supercomputers in the world. And at times I got to have 1/3 of it or something. It was ridiculous. And what's quite striking about it is that it's actually small. For a supercomputer of that power, it's only like a big pantry or like a space sauna or something, and it certainly feels like a space sauna. But maybe what I'm aiming at is that even in my little microcosm, Moore's law sort of still applies, seems to still apply, and there seems to be only one direction, and that direction is up. So, and now into a couple of examples to show what I've been talking about. First, the grinding part, then the sliding part. I can do a couple of things on my own, but not very much. So I need help from colleagues. So these are three. This is one former colleague, Davide Bianchi. He now works for IMS Nanofabrication. Ulrike Zirkbayer and Sabine Lehroch are two colleagues from work at ACT Research in Wiener Neustadt. And this is my former PhD, well, he's my PhD advisor, but of course I got my PhD, I don't know, in 2012 or something. But since he lived in the city where ACT is based, he used to come for a coffee every now and then. We'd chat, he'd ask some very difficult questions, and this led to a paper or two. Unfortunately, he passed away 2 months ago, so Gerhard, wherever you are, I'm missing you. So this would represent my first shot at making my own polycrystalline system from scratch. So this is basically the pure mathematics behind it, the Voronoi construction, where you try to make a system that can be periodically replicated, so you don't get into boundary trouble with DMD. I'm going to show you a little bit later what this would actually look like in a grinding system. But what we also need is something to grind against that, and this would be the abrasives. These would be based on a cubic lattice, some very simple basic geometries, but you can combine those, you can cleave along crystallographic planes, and you can get a lot of different geometries. You can get more spherical ones like these truncated octahedra or these cubo-octahedral, but you can go, let's say, full parameterization into plate-like particles, rod-like particles. However, these still have a cubic lattice. These down here are more recent. Those are actually alumina, chemically, and let's say from the shape. You'll see here how I distribute them over the surface, make sure they don't overlap, and so on. Then I shake hard. I make sure that they are jumbled and meet the work piece at random orientations, random rake angles, and then I start grinding away. So this would be about 3 years old, 2 to 3 years old. What this would look like, this is the 60 by 60 by 30 nanocrystalline system. So this would be grinding nanocrystalline iron with cubo-octahedral abrasives. Now you do that for several loads, you do that for several sets of boundary conditions. And then of course you want to know what came out. So you have to evaluate the system, you have to evaluate your output. You might record some forces, you might record other quantities, centers of mass of certain particles. But the most important thing is, of course, the geometry. You want to know which atom was where and at what point in time. And then you can push that through a visualization tool, which is still open source, named Ovito. That can do polyhedral template matching to get the orientations of the grains. It can do dislocation analysis. It's a very powerful tool. And by doing that and then visualizing, I can actually make sections that look very much like an EBSD picture that a material scientist might get from cutting a fib lamella, putting it into the SEM and waiting for a couple of hours until they get a high resolution EBSD image. So those are very popular with the material scientist crowd. And they are extremely good for observing phenomena like lattice rotation, the formation of grain boundaries, even low-angle grain boundaries. You can see twinning, you can see defects. It's really quite, the material scientists really feel at home with this. So if I look one step further, this would be a more recent example where 10 of these slices that are equally spaced through my system, where you see how the alumina abrasives basically cut a chip out of the workpiece. And you can take a look at chip morphology. You can see how the grains arrange, how fine-grained actually the chips are, how the dislocations come from the surface, from either the leading or the trailing edge of the abrasive into the surface. You can check if they are stored in the grains. You can see if the surface sort of gets annealed afterwards. If something seems funny to you, sometimes the grains or the abrasives seem to be coming sideways a little bit because these slices are only 2 monolayers thick. It's because my abrasives are going at a slight angle to the x-axis of my system so that they scan a larger portion of the system more evenly, because as you saw before, it's periodic. So they go out let's say the right side of the system, they come back in Pac-Man wise on the left side, and I don't want them to keep grinding in their own grind marks. So they will be moving slightly up and basically scanning the entire system. So there's a lot to be seen here for material scientists, but so far this has only been, let's say, looking at micrographs. You can do a lot from that, but MD is good for more than just that. However, before I have to come, let's say, to one of the legacies of my PhD advisor, he visited me once and said, but you know that, there are pitfalls, and did you think of properly getting rid of that immense amount of heat that you're putting into the system? And one other reviewer had already mentioned that, and I said, yeah, you're actually right. We really should take a look into that. Because there are 2 standard approaches in MD how to thermalize your system and how to dissipate the heat. One of them that I will call now base thermostating is basically you emulate the bulk down here. You say all heat has to vanish from here, and from up here to down there, I'll just let the atoms do their thing. That has one huge drawback. MD doesn't have electrons. So you only have phononic dissipation of the heat, only phononic heat transfer. And that's not good enough in metallic systems because there the electrons dominate. Apparently my arrow keeps disappearing. So then there's a second variant, which I will call fully thermostated, where people go fully ballistic and thermostat the heck out of their system. The problem there is that the heat gets removed instantaneously and you don't have any gradients in there, which is also not very realistic. So you want to be somewhere in between, but how much in between is good? You see here, these are the contact spots where the abrasives touch the workpiece. This is base thermostated, this is fully thermostated. They don't fit together, they're both wrong. So what are we going to do? So he showed me some old papers that of a former colleague of his. And it turns out there's a very simple, straightforward way of doing this. You just have to do it. And that is you emulate the bulk with one heat sink at the very bottom. And then you have a separate parallel heat bath that basically does the electron-phonon coupling. So that couples your electrons to the phonons with a certain coupling constant, coupling time. And it is your job as the scientist to find out what is that coupling time to get it just right, so this behaves like a metal workpiece. So this is what, and we had to write a whole paper about that because it turns out to be. It seems simple, but to describe it right, you have to do it properly. And you can get a good, let's say, first guess from the Sommerfeld theory for metals for this lambda. But all of the papers that I read say, yeah, it's a guess, but you're going to be off by at least a factor of 2 or 3. Yeah. So you have to do your own simulations. So you do some preemptive simulations. You do you try out a couple of lambdas, and you measure these gradients. And as you measure these gradients, you can just plug that into Fourier's law, and you can back out a kappa, the heat conductivity in your system, and then basically from there on you brute force your way through, and in the end you get a fit and find that coupling time that corresponds to the metal that you're trying to simulate macroscopically. In this case, metal, and it turns out that for metal, for iron, it's 3.5 picoseconds of coupling time, and that I just put into my simulation, and voila, I get the correct gradients for the heat dissipation. So that out of the way, we can now start, doing some material science, and this is where I basically have to hand all my data over to a colleague. And my colleague Ulrike looked at lots of videos, and you go all googly-eyed from looking at that many videos, but then she found a couple of interesting events that she wanted me to, let's say, resolve for her a little bit. So here she sees we're looking at this blue grain here, and the blue grain, let's say the pink one here gets abraded to a certain point where the grain boundary sort of moves up towards the surface. The blue grain starts growing, which you see here. And then suddenly there's a rotation and the formation of a low-angle grain boundary. And she was wondering, okay, can you show me a little bit more about how this came about? So we flip into another view, we put on our augmented reality goggles, and we look at the atomic advection velocities in that system. So all the atoms are replaced now by little arrows showing where they want to go at the moment. And we're zooming in on the low velocities. So we know up here it's 80 meters per second, it's very fast. Down here, we're looking only at velocities between 0 and 10 meters per second, which is still fast tribologically, but if you're grinding across so fast, this is actually, let's say, relatively slow. And here we can see how the atoms within the grains start drifting. And actually here, this is where you see it. Here's actually a vortex forming that that initiates this lattice rotation. And here's where it's finished. And this situation here is exactly the point that she's circled here. Whereas then we also looked at the stress tensor component. So this would be back to you, Rob, basically. Yes, MD can do that. It's a finicky thing because it's only defined up to an atomic volume. So you would have to know the volume of your atom to get the exact stresses. But this is good enough for now to see where we have lots of stress and where we have little stress. And here you also see that in that particular grain, just before the rotation, before the lattice rotation, there was a high amount of stress, and then it rotated, the low angle grain boundary formed, and the stress was relieved. So then you can follow the system a little further. I'm not going to go through all the details. That's basically her field. But you can see that low angle grain boundary becomes a higher angle grain boundary and so on. And then the grain refines even further. So at the end, we have several small grains where before we had basically one. And those are just some of the things that you can get out of the MD of this sort of system. You can quantify it as well. What we did recently, let's say when we upped our game a little bit, is not make our own polycrystalline system, but let somebody else basically do it who really knows what they're doing. And Tony Rollett is co-author of a tool called Dream 3D that basically synthesizes microstructures based on a set of statistics. And it doesn't care how large your system really is. It just makes sure that this is, let's say, that this makes sense in a microstructural sort of way. And then I had to program my own conversion routine that basically reads this structure and makes it into something that my MD code can read. So basically, I make this into alpha shapes. I fill the alpha shapes with the lattice that I want to put in there. And this already gives me the orientation. So this already makes sure that there are not too many low angle grain boundaries and so on. And then I just cleave somewhere where I want to have the surface. I anneal it to make sure that it's in thermodynamic equilibrium. And then I add some alumina abrasives on top and I start grinding. And this is pretty much the point where we are at with the grinding simulations. So this is already the large system, 25 million atoms. And we are currently working on a large-scale grinding parameter study where we vary the workpiece material between soft ferrite and slightly harder mild carbon steel, but the same microstructure only with the second phase replaced by cementite in the steel. We change the abrasive sizes, the number of abrasives, the shape of the abrasives. We juxtapose the sharp abrasives with more ellipsoidal ones that look a little bit more like fisherman's friends. We change the in-feed depth. So of course we see if we indent further and further, how does the workpiece change? Does it change anything in the microstructure? We look at the temperature, basically a study in cooling efficiency. And we also play around with displacement controlled, where we indent to a certain depth, and load controlled. I should be hurrying up, right? So just as a little example to see the difference, how blunt abrasives that are well cooled and sharp abrasives that are not cooled very well while they're grinding at the workpiece, how this changes the microstructure. What we see here is just a plot of the grain boundary and dislocation fraction in the system. And you see here that closer to red means more grain boundaries, more dislocations. It basically shows that these surface grains refine more, have more dislocations, may harden up. Whereas here with the sharp abrasives, it's basically cut, the material removed is cut off And due to the higher temperature, it actually heals out and we don't have any grain refinement here. So, second block. Sorry, I should go back once more because I have a couple of other colleagues there. So here's Manel, another colleague of mine, Carsten, the professor of the tribology group at TU Vienna, and Daniele Dini, who we showed this, and he latched onto it and was in love with it right away. So here's a system that we're not going to grind on, but that we're actually going to slide upon. And this is a study in alloys. So we have copper, we have pure nickel, and we have 3 alloys in between. And we're going to change the stacking fault energy by changing the alloying of these between these 2 metals. And then we're going to press a rough iron surface against it and start rubbing. We made sure that our grains are large enough that we have 40 nanometer grains so that our plasticity is not dominated by grain boundary sliding. So we're solidly in the Hall Petch regime. And only at 300 Kelvin, only at room temperature, we already blew 4 million core hours on this little project. So this is a little bit of a movie of what such a system that is highly loaded, mind you, might look from the side as we're rubbing with the rough surface at it. And I'll show you a couple of the phenomena or a couple of the mechanisms that we see. If you don't press too hard or if you have a high nickel content, you have incipient twinning, you have lattice rotation a little bit. As you push harder or the copper content goes up, you have more grain boundary dominated processes, you have grain refinement. As you push even further, you experience massive twinning, and which is followed by stress-induced grain growth. And finally, we come to the limits of our system. At some point, the shear layer that starts forming elongates your grains and it dominates the behavior of your entire system. Basically, you have sort of a couette-like flow. It's more like peanut butter at this stage. So basically, we've hit the end of what we can simulate with a thickness of 40 nanometers. And usually, explaining all of this takes about half an hour. So I'm going to give you the 1.5 minute summary. So we start out, when we look at all of our simulation runs in the end, we look at EBSD visualizations, we look at grain boundary and twins and stacking fault visualizations, we look at atomic advection velocity visualizations where we see the shear layer evolving, and we look at the stress visualizations. And then we start to distill it. So first we eliminate the lateral resolution of our system, and we produce these maps where we have time in the horizontal axis and the sample depth in the vertical axis. And then we can put quantities like the stress in shear direction, or as seen here in the heat map, or these lines here represent the twinning activity in the sample over time. And this is for 4 different loads. And as we simplify that a little bit, we get one quantity of interest that we track over time. So we have time-dependent curves of some quantity that we're interested in this case, the formation of twins. Then we eliminate the time as a second thing. So we look at these graphs, we see, there's something interesting going on here. We're going to check out when exactly the twinning activity takes off. So this is what's plotted here as an example of something that you can plot as a function of the normal pressure, normal load. And so this would be the distance that it takes that you have to slide until, for this type of system, the twinning activity starts to surge, starts to transit. And then you can fit curves into these load dependencies, and you will always wind up with some typical normal stress that is typical for this alloy and for this, let's say, process or phenomenon, or ideally a mechanism. And then you can associate those and feed those after the elimination of load, feed those into this 2-dimensional map where you have the alloying, let's say the composition on the horizontal axis, the normal pressure on the vertical axis, and then it basically nicely falls apart into regimes where you have purely elastic deformation, twinning and incipient twinning and lattice rotation, you have grain refinement, massive twinning and stress-induced grain growth, and the point where the shear layer just dominates your entire system. And we are hoping that this might be generalized at some point. We're not there yet, but this is currently under review. We're not there yet, but we hope that this will be generalized and that this can become, let's say, an almost direct engineering application of MD in some near future, hopefully this decade. Unfortunately, I think because I'm already a little bit late, I will be skipping the Bauschinger part, which is also a nice example of how you slide in one direction, then you reverse the sliding direction, and much of the plastic deformation that you got in your iron sample here, for example, sort of gets ironed out. If you catch my drift. So you see here the grain refinement, and as you reverse your sliding, the grain refinement becomes grain coarsening again, which is basically computational evidence of a tribological Bauschinger effect. And so I'm not going to go into the details of that, but here's my upshot and my outlook. So I hope by now you'll at least sort of agree that MD is becoming big enough with these supercomputers that we have, that we can do a meaningful analysis of microstructural evolution, even sort of macroscopic-like. Yeah? As long as your grains are large enough, they will sort of behave like macroscopic grains, so you will see all this behavior. And just make sure that if you're sliding very fast, that you dissipate the heat in a meaningful way, so that you don't have any obvious artifacts just from the way that you're taking the heat out of the system. So it turns out that even now, MD can be applied to study phenomena such as work hardening or grain coarsening in a tribological context. But I hope that soon, with enough data, if we perform lots of these simulations in parallel and make it in a very consistent way, that we can get surface engineering relevant results, even for such a messy system. So actually, from an MD point of view, such a system is extremely messy. But if you distill your data wisely, then you can actually get very meaningful, scalable trends. And this is where I'd like to stop. And thank you for your attention.
Thank you very much, Stefan. Another really interesting talk. Probably got time for a quick couple of questions. So I've got a couple from Hande Toffoli, who has some questions on the thermostatting. So for the electron-phonon coupling, could you comment on how using a single lifetime for all of the phonon modes gets efficient and correct dissipation? And also kind of back up one. And do you get any phononic reflection from the lower boundary back into the system?
Okay, so those are pretty tricky questions. I'll have you know. So you don't get all the modes. Basically, you're weaseling your way through, and that's why it's so simple. But it works well enough. Okay. Actually, it turns out that the full thermostatting is relatively close to reality, but not close enough. So if you can do better, why not try? You're basically just fitting to the macroscopic heat conductivity, and leave it at that. So you don't do that. And about the phononic reflections, I would say that since the heat sink down here is very strong, I would say it just sucks it up. That would be my short question. For a better answer, I think I would have to think a little more.
Thanks. And another very quick one, much quicker one, this one. Could you just give us some details about the interatomic potential you used for the simulations with cement pipe? Sebastian at Berry Resto.
This is, it's a Tersov potential. And, a Swedish group, Tersov potential 2009. I can't think of the main author. I'll put that in the chat or so later on. But it is a Tersov potential, and it technically can even do chromium. But at that time, it becomes a can of worms, because then you have, 27 different parameter sets. So it gets complicated. If you're just doing cementite and iron, it is manageable.
Mm-hmm. Yeah. Okay. Thanks again, Stefan, for another great talk. I'll just hand over to Chiara to close the meeting and let you know about next week's seminar and going forward. And then, we'll call it a day for today. Thanks.
Thank you very much to both Stefan and Rob for their great talks. So I hope to see you all again virtually next week when we will hear from Dr. Ian Taylor from Shell about challenges for lubricants in the next 10 years, and Professor James Battis from Texas A&M University about friction and energy dissipation in 2D materials. And so once again, the talks that you just saw will then go on the YouTube channel and on our website. So if your questions didn't get answered, or if you have more questions, please ask them there in the comments, either on the website or under the YouTube video. And I again just want to encourage you to think about submitting a poster for the Twitter Poster Conference on the 11th of June. And with this, I thank you all very much for joining and asking great questions, and I hope that you'll join us again next week. Bye bye.